Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I am at the Space Telescope Science Institute, and with me today is again, with one of our Hangouts, Dr. Mario Livio and Dr. Carol Christian from the Space Telescope Science Institute. They've done many Hangouts with me before on this, but we're also joined by Dr. Eva Villaver from, and let me get this right, Universidad Autónoma de Madrid. She's an astronomer, and she is attending a symposium that we're having at the Institute this week that is, I think, one of the more interesting things we've had here at the Space Telescope Science Institute. They are discussing and meeting this week to talk about issues associated with habitability. Habitability around planets, moons, what does something mean to be habitable, and habitable for whom? I mean, what are the conditions that are necessary to have life out in the universe? And an issue that I'm particularly interested in also is how extensible is Earth's habitability requirements to everything else. And so astronomers are meeting, discussing all these really great questions, and we're going to touch on some of this right now. With this hangout. Mario and Eva were very kind to give us some of their time, and Carol's with us to give her perspective, which is always really good, to discuss this idea of habitability. So before I get started, I want to let you know I'm monitoring YouTube, I'm monitoring Google+, and if you want to tweet some questions or comments using the Hubble Hangout hashtag, I'm also monitoring those as well, and we'll try to get to them if there's time at the end. We only have a half an hour, so I want to just jump right in. Habitability. Habitability. All this time I had Mario and Eva big instead of me. Let's talk about what we mean by that. And so Mario, what's your impression? When we say habitable, what goes in your head? Are we talking about Earth? Are we talking about mammals, microbes? What do we mean by habitability?
No, so unfortunately, since we only so far discovered life on Earth, so we made a definition of what we mean by habitable. So basically, around every star, you can define a range of distances from the star which allows for liquid water on the surface of that planet. If there is a planet there, then liquid water can exist. In the particular case of the Earth, of course, the Earth is in the habitable zone around our star, namely the Sun. But because we think that water may be absolutely essential for life, we define this region for any planet around any other star, and then we've searched to see whether there are any planets in this habitable zone, namely in that region that would allow for liquid water to be on the surface of that planet.
So this week there are a lot of talks being given in a wide variety on wide varieties of subjects, and we're looking at every single possibility. So surely liquid water isn't the only real thing that one would need, right? I mean, is that the defining characteristic of a habitable place, a place where life can exist? Is that the only thing you guys are looking at?
Well, I can jump in here a little bit. That's the classic definition, but of course, when you think about it, that is very Earth-centric. And of course, we're looking at Mars to see if it is habitable or was habitable, and it's thought that it did have water. Now, of course, the star can change. The parent star, like we have our Sun, it changes very slowly. There are other stars that change more rapidly, and there are stars that change more slowly in their lifetimes. So you're right, the habitability can change. So for a star that lives very fast, there might be a region that is what fits our definition of habitable, but because the star changes its brightness and energy so fast, there's no chance that life will evolve. And then there are other stars, planets possibly around stars that take a very long time and are very stable, and there's lots of chances that they could have a habitable area. So for a moment in time, the fact that a planet might be habitable does not mean, okay, now life is going to form for sure. But it's a starting place. It's a starting place.
It's a starting place. But as I look at the talks of some of these things that people were given, there was one on whether Ceres, the dwarf planet Ceres, is habitable, and you know, there's talking, you know, and Ava's talk was also about, in which we're going to get to here in a little bit more detail, even about what is the survivability of, I mean, of going through a main sequence when the star leaves the main sequence and becomes a red giant. What's the survivability of that, and is there any chance for them to come back? So we're looking way beyond liquid water here, and so it's a really important, I think, in-depth look at this whole concept, because it really, one of the things that I always get when I talk to people or we do stories on exoplanets is, why are we always so concerned about liquid water? Why can't you have like a sulfuric acid oceans or a Venus-like place with life? Isn't it possible? Well, sure it is, but you know, is it likely? And when we know what is likely is the fact that we start with Earth. That's our one data point. So Ava, let me get you into this conversation. What do you think of this idea of habitability in general? Do you think, for example, that the Earth is typical? Are there a lot of us out? Are there a lot of planets like ours out there?
Well, in fact, this is one of the most important parameters that we are trying to determine. What is the percentage of planets of stars out there that have planets like Earth at the right distance? And that's a very important question to answer, because once we have this number, we can assess what is the percentage of stars out there that might have at least a planet with the right conditions at the right distance in order to be able to host life. And as you mentioned, yes, we look into liquid water because this is what we know, but there might be other dissolvents that are good for life. The good thing about water is that it extends a broad range of conditions. I mean, we have more than 100 degrees between the point where the water freezes to the point where water gets evaporated, and that's good for life. Other forms of life might exist, for example, in a methane kind of dissolvent, but that would be hard to look for. I mean, we have to start with the basic things and build up slowly from there.
Okay, so you guys, and when in your talk this afternoon, I saw that you had a lot of references to work that you had done with Mario. So presumably, you guys have looked into this research of habitability in post-main sequence stars before. So let's go into that a little bit. Your talk was called "Are Post-Main Sequence Planets Doomed?" And you were but let's talk about what we mean by that. What is a post-main sequence star? Can you describe it for us?
Yes, as you know, I mean, we are orbiting a star that is burning hydrogen in the core, but the star will eventually run out of hydrogen. And as soon as that happens, it will move into a different evolutionary stage. For a star, in order to fight gravity, it has to burn something, either in the core or in a shell outside of the core. The next nuclear fuel that a star like the Sun can burn is helium, and that's it. It cannot burn anything else. So we talk about
its mass, or
yes,
what?
Yes,
okay.
Just because of its mass. If it were a more massive star, it will be able to burn much higher elements. But a star like the Sun, it will stop after helium. It will build a carbon-oxygen core, and it will have the envelope removed by processes like winds. And this is exactly what we mean by a post-main sequence star. A main sequence star is a star that is burning hydrogen. Post-main sequence is that it has run out of hydrogen in the core, and it goes through a very, let's say, not stable phases of evolution.
It starts to get big, right? It starts to expand and get larger, right? When it turns into a red giant.
Yes. Yes.
Okay.
So I was just going to say, main sequence refers to the majority of the time the star spends in a stable state, and we call that main sequence. For different stars of different masses, the amount of time that occurs is different. Luckily for us, for the Sun, it's a long time. And then post-main sequence is, as Eva said, now you've got problems in the core, you've exhausted some of the fuel, and now the structure of the star is trying to readjust to its circumstance. It's got gravity pushing in, energy pushing out, and that isn't so good for a planet that is out in orbit around that star.
Okay, so Mario, did you do some work with? Did you and Ava work together earlier on some of these questions as well? I saw your name on a lot of slides.
Yeah, we started working on this. I don't know, around 2005, 6. I think maybe published our first work in 2007 or thereabouts, and then published a few more works following that. So the idea is very simple. Since we now know that most stars have planets around them, the question is, what happens to these planets as the star, as we said, exhausts its hydrogen? And a star like the sun is going to increase in radius, by factor of hundreds when it becomes a red giant star.
Out past the orbit of Earth, presumably.
Well, actually, the Earth turns out to be the most difficult thing to calculate. While it's true that the sun can outpass the current orbit of Earth, Earth itself might move a little bit outwards by that time.
Oh, that's right, of course, yes.
Yeah.
Yes.
So it's a touch and go what will actually happen to Earth. But let's talk more generally about many of these planets that are in there. So now you have this giant star, and you have a planet that was not directly engulfed in it. It was just was left there. But what happens at that point, according to our calculations, is that the planet raises tides on the star, just like the moon raises tides on the Earth. And as it raises those tides, the orbit starts to dissipate and the planet starts to move inward. And we wanted to know which planets would actually be eventually engulfed by the star, which planets would manage to survive, and so on. So, for example, the Earth really turns out to be at that touch and go place where some calculations show that it will be eventually engulfed, some show that it may just barely survive. Now, planets, of course, that are farther than where the Earth is now will survive. But even if they survive in terms of, that physically they are still there, that doesn't mean that life on them can survive.
Exactly.
For example, the Earth will be scorched. I mean, even if it's not engulfed, it will be totally scorched. So there are all these deep questions as to what happens to, if there is life on any kinds of these planets, what happens to them as their stars evolve.
So Ava, in your talk, you actually addressed that. Your talk was split up into two main parts, as I understood it. You were trying to answer the question, what would life have to endure after this, what Mario just described, happened? What would life have to go through to survive it, presumably, if it even could? And the second question you were asking is, are there any suitable conditions that might form after the red giant phase that might give life a second chance to start up on Earth? And can you comment on that a little bit, especially to the first point? What would life have to endure to get to survive the red giant phase, if it even could? And do you think it could?
Well, first of all, before even the star leaves the main sequence, this stage of evolution where the sun is stable, the luminosity of the sun will increase. I mean, the energy that the sun will emit per second is going to increase. And
so
this
the sky is going to get a lot brighter on Earth.
Exactly. And that will have... I mean, it's not clear whether the atmosphere will be able to adjust to the changes provided by the increasing luminosity of the sun over the time span that it will happen, but most likely not. I mean, most likely the atmosphere will get
because the solar wind will be also increased quite a bit too. Is that right?
Yes.
Yes. Yeah, and the radiation of all kinds, I suppose.
But we have the magnetic field from the Earth that will protect it from the solar wind. So the solar wind is not such a big problem. It's the increase of the energy of the emitted by the sun that will make this planet a very hot place, and we will have probably a runaway effect like the one that happened in Venus and got rid of the atmosphere. So that will be the first thing before even the sun gets bigger. Then the sun will start to get bigger in radius. So we are going to have a planet that it might move outwards a little bit, but we have the surface of the sun that will be approaching us. as the sun evolves. So we are going to get very close to the surface of the sun in principle. That is another of the things that life will have to endure if it has already managed to survive the increase of luminosity. If
So
it
an
doesn't,
increase in luminosity, we're going to get closer to the star. Or the star is going to get closer to us.
yes, we might get that close that we might even get inside of the sun. And if we get inside of the sun, forget it. I mean, the planet will eventually spiral in very quickly, and it will merge with the core of the star. So that will be.
That would have to be some pretty robust life to make it through that, I suppose.
Yes. 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 So if the planet managed to survive this phase, then it will be a very stable phase following that of helium burning in the core, in which if life had managed to survive somehow, it might be able to have a second chance to develop, or to enjoy a few more giga years.
It's better to move before it's too late.
Yes.
Yeah. Well, luckily we've got some time. When let's just go ahead and say when you're when is this expected to happen with our sun?
In about 5 billion years.
Oh, good. So, all right. So there's no immediate cause for alarm, at least right now. But the fact that you're looking at this in a bigger picture is really fascinating to me. I mean, you're looking at not just, I mean, obviously I like to bring it home because Earth is a typical thing that we can, visualize, and so to see how our sun evolves and what might happen to life here is an important one. But in your talk, you used a really scary term called, I remember laughing when I saw it, planet evaporation rates. Yikes. So why don't you tell us? So what does that mean? The planet these are when planets just simply don't survive.
Yes, this is a different phase of evolution that a planet will have to endure after the post-main sequence, and it's the planetary nebula phase, in which we have a very huge flux of radiation that is in the ultraviolet. So we have the ozone layer now protecting us from the ultraviolet radiation from the sun. Imagine a radiation that is much, much, much higher, orders of magnitude higher, in a star that has evolved of the main sequence. And this radiation has so much energy that literally evaporates the surface of a planet, of a gas planet. And this is the calculation we made.
The ultraviolet energy from a planetary nebula can evaporate a planet. Carol, can you give a little background on a planetary nebula? What's she talking about when she says that?
I couldn't understand the question.
Sorry.
You're breaking up, Tony.
Yeah, you've been breaking up. Yeah,
Hello?
we couldn't hear the question.
Can I ask a question while we figure that out? My question to Eva and Mario is that I know, so you have this phase where the surface, the sun is getting bigger, or stars like the sun is getting bigger, and then you talk about, okay, that may be the demise of Earth. But what about like moons and planets that are further out that may have water on them? What happens to them? Because presumably they get warmer, and I know there are some people that are interested in, what could happen to a moon that has ice on it now? Will it have water, and will it be in that state long enough for even the tiniest microbe to form?
Well, as the sun evolves, the habitability zone will move outwards. So it will reach the region where we can have we can have planets with moons out there where life can be sustainable. You have to keep in mind that the phases of evolution after the main sequence are shorter. So we are going to talk about of the order of
1 billion years.
1 billion years.
Yeah.
So
it's not long enough. Probably.
It's not long enough.
Maybe for microbes, yes,
yes.
but for elephants, probably
not.
Am I back, guys? Can you see me? Okay?
Yeah, we hear you.
Okay. Yeah. All right. What I wanted to get into right there was planetary nebula. I wanted to go back to that idea, and I wanted Carol to kind of explain how the Earth gets, or how the sun gets to a planetary nebula. Just give us a little background on it, in case people don't know what that is.
So just about the term, astronomers are you know, when they look through the telescope and they see something and it reminds them of something else, a word comes out of their mouth and it may not have astrophysical significance. So planetary nebula were thought to be, when they were first seen through a telescope, a star with some kind of planetary system around it. Well, it turns out they're actually nebula, and they really have nothing to do with planets, or probably don't have. I mean, that's not their main function. Actually, Mario is an expert on this. But anyway, the idea is, as they've been discussing, Eva and Mario have been discussing, the core of the star collapses. It starts to push its outer atmosphere out. It gets bigger. It's pumping out energy. At some point, it may have a more dramatic structure rearrangement, which will force the outer part, a lot of the material in the outer part of the star. It won't explode per se, but it will push a lot of material out. And we used to think that was a nice little gentle process, and it's a nice spherical nebula. Well, it turns out with Hubble, we found out that the structures of planetary nebula are quite complicated, and that process of readjusting the structure is complicated, but gives rise to, I think, some of the most beautiful nebula we have imaged with Hubble. So Mario and Eva can take it from there.
Yeah, let me just add that, you know, just to this last point that Carol made, that, you know, if you look at some of the most fantastic images that Hubble has taken, they are of planetary nebulae. Because what happens is this, as these outer layers are pushed into space, you expose this hot core that Eva was talking about, which emits this ultraviolet radiation, and that really heats all this gas that was ejected, and it causes it to fluoresce. And so you see all these fantastic colors in it, and really those are truly breathtaking images of these planetary nebulae, and they are all different. I mean, you know, like snowflakes. Each one of them looks differently.
A very famous example, for those of you who want to know, is the Ring Nebula. That's a very famous planetary nebula. It looks like a smoke ring in space. While we're on this,
that's the one I learned about in fourth. I always say I learned about that in fourth grade, and everybody thought it was a nice uniform, as you said, smoke ring. But actually, when you look at it in the Hubble images in detail, it has all kinds of very interesting, intricate
deceiving.
structures.
The structure is deceiving.
Yeah, it's fabulous.
Sure. So Ava, in your talk on this subject, you said that the bad thing is that planets tend to evaporate inside them, but
Tony, you're breaking up again.
I didn't quite get the sense of your question.
Okay, so in your am I okay now?
Yes, you are.
Yeah.
Okay.
In your talk, with planetary nebula, you said the bad thing is that planets tend to evaporate inside of them, but there's a good side to it, and the good side is that there's also lots of really good complex molecules inside these things. Do you think that for planets that survive, that don't manage to evaporate, there might be something there for them to work with?
Yeah, I think, I mean, we are made of carbon after all, and one of the main producers of carbon in space are stars like the Sun that evolve into the planetary nebula stage. So the fact that we have carbon producers building big molecules of, as I mentioned, it was carbon-60 Fullerene molecules out there, I think this is good news for life, and all the material we are made of at the end came from the interior of stars, and these stars are literally bringing the byproducts of nucleosynthesis into the interstellar medium again, where the next generation of stars and planets is formed. So if we have already complex material over there, and we have a chance in order to build planets around these systems, that we don't have to wait for the next generation of stars to build the next generation of planets, I think that's good news for life.
Well, what about the water question, though? I mean, the conditions inside these nebula, and even after that phase, are we going to get water back, or is it gone forever? Does it survive? How does it survive?
Well, not where it's very hot. You will not get it where it's very hot. But as we said, I mean, you know, the habitable zone moves outwards as that star evolves and becomes more luminous and hotter. So there will be some region which is farther out, which could still have water.
Okay, and so what are we left with after this phase? After the planetary nebula phase, we're left with
The
a
white dwarf.
white dwarf, right. So hopefully we've got a white dwarf star with some planets in a stable orbit that survived everything somewhere near a new habitable zone. Is there a time scale that is conducive to life reforming here?
It is a time scale if we are very close to the star, and the problem is that it's very hard to bring a planet that close to the star at that point, because as I mentioned in my talk, every planet that we expect out of these systems are going to be very far away. So we have to build a mechanism in order to throw a planet close to the white dwarf, and that's a very unlikely process, but it may happen. I mean,
Okay.
as we know, life is a very unlikely process, and we are here, so that's something to keep in mind.
Well, that's a question, isn't it? That's one of the things I wanted to address. In my opinion, life is either incredibly easy to bring about, or it's very, very hard. And there are all kinds of, I've always wondered, what does it take to go from a system with zero life, no life whatsoever, to having life? Like amino acids might form in an early Earth, or we might get all kinds of gases and primordial soups and everything that won't be alive.
So
But then one day we wake up and there's life in there. That step, going from something that's not alive to something that's live, I want to know how hard that is.
So that first step, it appears to be, at least from the one example we have on Earth, appears to be not that hard, that very first step. And the reason I say this is, there are two reasons really. One is that life on Earth appeared almost as soon as it could have appeared. Namely, the very, very early Earth, things were very hot, there was a lot of bombardment and so on by all kinds of asteroids and meteors and whatnot and so on. But as soon as the situation stabilized a little bit, we find already signs to life. So clearly on Earth, it didn't take too long for life to appear. The second reason I say that first step may not be hard is that I have a friend, Jack Szostak, who is a Nobel laureate who works at Harvard in trying to produce life in the lab. And the last time I asked him, so how long you think it will be before you actually can produce life in the lab? And his answer was about 5 years. So, if you can produce, So if you can produce life in the lab, it means it's really not that hard. Now, again, if you take a lesson from Earth, and you should be very careful doing this, because Earth is one example, then the step to get from very primitive life to very complex life, that actually took a long time on Earth, billions of years, and also required all kinds of fine-tunings and chance events and so on. So that may be the part that's really hard.
Wow, there's a hangout I need to have. We need to get you and Seth together and talk about this more in depth at some point in the future. That sounds like a great one. Okay, so we're out of time, but I want to get to one quick question. Brian Katnoff on the Q&A app is asking, can organisms survive off gases other than oxygen and CO2? Who wants to take that one?
Well, I mean, yeah, I'm a great expert on this. I only know I don't know a little bit about this, but there are actually there are quite a number of biologists who are working on these questions, and there's another kind of survivability that they are interested in. It's not so much the planet survivability. They are interested in the survivability and adaptability of organisms. And so there do seem to be some organisms that can adapt to what we would consider a very hostile living environment. But they are organisms. They are not elephants.
Right, and those are called extremophiles, aren't they?
Right. And so as far as Mario and Eva may know different, but as far as I know, there has not been any building blocks of life formed in one of those adverse environments. But the biologists who are looking at something called extremophiles are studying whether life can A, adapt, or B, survive conditions. And that goes back a little bit to the question you asked, is that these catastrophic events happen maybe in the outer solar system, microbes form, then they freeze or they get hot. Can they survive and then come back to life? And they're trying to study that. And there are microorganisms that hibernate in really horrific conditions, you know, and
Here on Earth, that's right.
really nasty chemicals, and they can be revived at different temperatures. So it's an active area of study.
Yeah, okay, one more, and then I'll let you guys go. This one is from Hugo Burnham, who's going, and this one I'll address to you, Eva, you might know. Is there something similar to the Hertzsprung-Russell diagram, but for planets instead of stars?
Yes, we are I mean, no, yes and no. I mean,
well, we have Jupiter-like planets. You've got rocky or super Earths, and
yeah, the Hertzsprung-Russell diagram is a question of evolution determined by the nuclear source of the star. I mean, if we can look at the diagram for planets in terms of luminosity versus temperature that tell us how it's going to cool off, just provided that it has some energy source that remains radioactive energy release from the contraction of the planet and things like that. But those are much more simple tracks for a planet.
Oh, okay. All right. Well, I guess I'm going to go ahead and stop there because you guys have to get going, and there's just so much more I was hoping to be able to talk about. This is a hugely interesting subject. There is a symposium being held all week long here at the Institute. Many of the videos and talks are already posted. I put the link to those webcast videos on the event page here. It's webcast.stsci.edu, and you go there and you can watch these talks. You can many of them are already archived. Some of them aren't, but many of them are. I don't know if Ava's is up yet or not. She just gave it only about an hour ago, a little over an hour ago. So, but I highly encourage you guys to check out these talks if you're interested in this question of habitability, because it's being looked at and discussed very seriously by astronomers right now at the Space Telescope Science Institute. So I'm going to stop here, guys. I want to thank Mario, Livio, and Ava, and Carol. All of you guys, thank you very much for joining me and talking about this. I will look for more Hubble Hangouts coming up in the future. I think our next one, Carol and I have scheduled, will be with Dr. Remy Sumer. We're going to be talking about looking at protoplanetary disks and exoplanets from NICMOS data and all kinds of other interesting topics. So look for those in the coming weeks and months ahead. Thank you all for watching, and as always, keep looking up.
Thank you.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I am at the Space Telescope Science Institute, and with me today is again, with one of our Hangouts, Dr. Mario Livio and Dr. Carol Christian from the Space Telescope Science Institute. They've done many Hangouts with me before on this, but we're also joined by Dr. Eva Villaver from, and let me get this right, Universidad Autónoma de Madrid. She's an astronomer, and she is attending a symposium that we're having at the Institute this week that is, I think, one of the more interesting things we've had here at the Space Telescope Science Institute. They are discussing and meeting this week to talk about issues associated with habitability. Habitability around planets, moons, what does something mean to be habitable, and habitable for whom? I mean, what are the conditions that are necessary to have life? Let's talk about what we mean by that. And so, Mario, what's your impression? When we say habitable, what goes in your head? Are we talking about Earth? Are we talking about mammals, microbes? What do we mean by habitability?
No, so unfortunately, since we only so far discovered life on Earth, so we made a definition of what we mean by habitable. So basically, around every star, you can define a range of distances from the star which allows for liquid water on the surface of that planet. If there is a planet there, then liquid water can exist. In the particular case of the Earth, of course, the Earth is in the habitable zone around our star, namely the Sun. But because we think that water may be absolutely essential for life, we define this region for any planet around any other star, and then we search to see whether there are any planets in this habitable zone, namely in that region that would allow for liquid water to be on the surface of that planet.
So this week there are a lot of talks being given in a wide variety of wide varieties of subjects, and we're looking at every single possibility. So surely liquid water isn't the only real thing that one would need, right? I mean, is that the defining characteristic of a habitable place, a place where life can exist? Is that the only thing you guys are looking at?
Well, I can jump in here a little bit. That's the classic definition, but of course, when you think about it, that is very Earth-centric. And of course, we're looking at Mars to see if it is habitable or was habitable, and it's thought that it did have water. Now, of course, the star can change. The parent star, like we have our sun, it changes very slowly. There are other stars that change more rapidly, and there are stars that change more slowly in their lifetimes. So you're right, the habitability can change. So for a star that lives very fast, there might be a region that is what fits our definition of habitable, but because the star changes its brightness and energy so fast, there's no chance that life will evolve. And then there are other stars, planets possibly around stars that take a very long time and are very stable, and there's lots of chances that they could have a habitable area. So for a moment in time, the fact that a planet might be habitable does not mean, okay, now life is going to form for sure. But it's a starting place. It's a starting place.
It's a starting place. But as I look at the talks of some of these things that people were given, there was one on whether Ceres, the dwarf planet Ceres, is habitable, and there's talking, and Ava's talk was also about, which we're going to get to here in a little bit more detail, even about what is out in the universe. And an issue that I'm particularly interested in also is how extensible is Earth's habitability requirements to everything else. And so astronomers are meeting, discussing all of these really great questions, and we're going to touch on some of this right now. With this hangout. Mario and Ava were very kind to give us some of their time, and Carol's with us to give her perspective, which is always really good, to discuss this idea of habitability. So before I get started, I want to let you know I'm monitoring YouTube, I'm monitoring Google+, and if you want to tweet some questions or comments using the Hubble Hangout hashtag, I'm also monitoring those as well, and we'll try to get to them if there's time at the end. We only have a half an hour, so I want to just jump right in. Habitability. Habitability. All this time I had Mario and Ava big instead of me. What